In this video, we'll take a look at related rates. So this is an application where we solve related variables. In this chapter, we study problems involving variables that are changing with respect to time. If two or more such variables are related to each other, then their rates change with respect to time are also related. For instance, let's pick a simple example. Suppose x and y are related by the equation y is equal to 2x. If both variables are changing with respect to time, then their rates of change will also be related. So when we say changing with respect to time, we're taking the derivative of y and the derivative of the x with respect to a new variable, which is t. So take the derivative, think of the chain rule again, dy, derivative of y is 1 dy dt is equal to 2 dx dt. So in the simple example, you can see that because y always has twice the value of x, it follows that the rate of change of y with respect to time is always twice the rate of change of x with respect to time. In other words, in certain practical problems, x and y are related by an equation that can be regarded as functions of a third variable t, which often represents time. Then we use implicit differentiation to relate dx dt and dy dt. This kind of problem is said to involve related rates. So let's think about an example. Let's take a look at a couple of examples. Example 1, if we drop a pebble into a calm pool of water, it causes ripples in the form of concentric circles, as shown. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of this disturbed water changing? So over time, if you've got your circle, over time, the circle has a radius and an area. And concentric circles means as the radius grows, the area is also growing. So what we want to figure out is at some particular point in time, what is the rate that the total area? We don't want to know what the total area is, we want to know the rate at which the area grows. So the first thing we do is figure out what formula from geometry are we going to use. So the area of a circle is pi times r squared. So our two variables are area and radius. So we're going to have two rates with respect to time. dA dt is going to be the rate of change of the area. dr dt is the rate of change of the radius. So what is our given rate? Again, a pebble is dropped, causing ripples. As shown, the radius of the outer ripple is increasing at a rate of 1 foot per second. So we're given that dr dt is 1 foot per second. Then we want to know at what rate is the area changing. So the rate to find, we want to find dA dt, the rate of change of the area over time. So the equation that relates our variables is our area of a circle formula. Area is equal to pi r squared. Then we're going to take the derivative of that function with respect to time. So we apply the chain rule. Again, time is not a variable that's present. So when we take the derivative of a, it's 1, and it's 1 dA dt. So the derivative of a with respect to time is dA dt equals derivative of pi r squared with respect to time is 2 pi r, that's the derivative of this term, times dr dt. That's the function that relates the rates of change of the radius in the area. And we got it by taking the derivative of the area formula. All right, then next step, basically what I like to do is substitute everything you have from the formula or given in the problem into this formula. So dA dt is what we're trying to find. So we don't have a value for dA dt. equals 2 times pi. We're given that the radius, let's see, it says the radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, so up here, when the radius is 4 feet, I want to know how fast is the area changing. So we substitute our radius is equal to 4, and dr dt is 1 foot per second. And I'll label the radius is 4 feet. Now we can go ahead and solve the problem. So we have 2 times pi times 4 times 1. So dA dt is equal to 8 pi. Feet times feet is square feet per second. So the area is increasing at a rate of 8 pi feet per square feet per second when the radius is 4 feet. So that's the exact value. Then if you want an approximation, you can go ahead and type 8 pi into the calculator. All right, so next question. Number 2, a tumor is modeled as being roughly spherical with radius r. So here's our sphere with radius r. If the radius of the tumor is currently r equals 0.54 centimeters and is increasing at the rate of 0.13 centimeters per month, what is the corresponding rate of change of the volume of the sphere? So in this case, we need to know the geometric formula for volume of a sphere. And volume of a sphere is equal to, I'll put it down here, 4/3 pi times r cubed. So the rate that we're given, since our equation relates the volume and the radius, there are two rates. There's a rate dV dt, how fast is the volume of the tumor growing, and there's a rate dr dt, how fast is the radius of the tumor growing. We're given that the radius is increasing at a rate of 0.13 centimeters per month, so we're given dr dt equals 0.13 centimeters per month. And we want to find is the rate of increase of the volume, so we want to find dV dt. So we take our equation of dV dt at when the radius is 0.54 centimeters. We're going to need that information for the next step. So think about the radius. As the radius is growing, then the sphere itself is growing. So we take the derivative of our volume equation with respect to time. So the derivative of v with respect to time is dv dt is equal to, take the derivative of 4/3 pi r to the third with respect to time. If you multiply the 3 in the front, we're left with 4 pi r squared times dr dt. Now that we have the derivative, this relates the speed of the radius and the speed of the volume, the rates of change. So now, instead of solving for the rate we're to find, we're going to go ahead and substitute our values in. dV dt is what we're looking for. It's already solved for dV dt. We get 4 times pi times the given radius, which was 0.54 centimeters squared, times dr dt, which was given in the problem. It was increasing at a rate of 0.13 centimeters per month. So we substitute in for dr dt 0.13 centimeters per month. So in this case, we're going to go ahead and multiply. Get the calculator. We're going to take, for exact value, 4 times 0.54 squared, because we're squaring the 0.54, times 0.13. And we end up with 0.151,632 pi centimeters squared times centimeters is cubic centimeters per month. Probably makes sense to multiply that out. So I'm going to go ahead and take the answer, multiply it by pi. So we take that answer, multiply it by, find your pi key on the calculator. So we get approximately 0.476 cubic centimeters per month is how fast the tumor is growing, the volume. All right, so there's two examples. Next example, we've got all edges E of a cube are expanding, this time we're expanding, at a rate of 3 centimeters per second. How fast is the volume changing when each edge is 10 centimeters? So we've got to start with the formula for volume of a cube. The volume of a cube is edge times edge times edge, which is e to the third. Okay. All right, so it says the edges, so our two rates are going to be dv dt. The volume of the cube is growing at a certain rate, and dE dt. The edges are growing at a certain rate. We're given that the edges are expanding at a rate of 3 centimeters per second. And we want to know how fast is the volume changing when each edge is 10 centimeters. So we're given a particular value of E, which is 10 centimeters. So take the derivative of the volume formula with respect to time. We get dV dt is equal to 3e squared times dE dt. So that's how the edge growth and the volume growth are related. And then substitute the values in that you know. So our volume, rate of growth of the volume is 3 times the edge, which is 10 centimeters squared, times the speed at which the edge is increasing, 3 centimeters per second. Multiply out, we get 3 times 100 square centimeters times 3 centimeters per second. And for exact, we get 3 times 100 times 3, which would be 900 cubic centimeters per second. So when the volume, or when the edge is at 10 centimeters, then the volume is growing at a rate at 900 cubic centimeters per second. If your cube was a cube of ice and it was melting, you would end up with a negative value because it would be shrinking. So if your rate of change is negative, then it's going to have a negative 3 centimeters per second. Last example. Here's one like one on homework. We have a man 5.5 feet tall approaches a street light 17 feet above the ground at a rate of 7 feet per second. So in the picture, the man is walking towards the street light at 7 feet per second. How fast is the end of the man's shadow moving when he's 7 feet from the base of the light? So think about physically, if the man is walking towards the street light is shining, and his shadow, the edge of his shadow is moving. So we're going to relate this in similar triangles. So think about the triangle that contains the man and his shadow. That triangle has a length. If we have the entire length, y, and the length as he's moving towards the street light is x, then the length in the smaller triangle is y minus x. Then think about the bigger triangle. Y is the longer side, 17, and we're going to set up an equation with similar triangles. So we have the two items that are moving are dx dt and dy dt. So dx dt represents the rate that the man is moving towards the street light, and that's 7 feet per second. Dy dt is this point back here. That's going to represent the rate at which his shadow is moving. So if we use similar triangles, you can set it up in a lot of different ways, but if you take 5.5 to 17, it's the ratio of two sides. The ratio of 5.5 to 17 is the same as the ratio of y minus x to y. Cross multiply, we get 5.5y is equal to 17 times y minus x. Multiply through, Here's 17. We'll get 17y minus 17x. Let's see, I can take the 17x to the other side and then subtract 5.5y from each side. 17 minus 5.5 is 11.5y. So this equation relates x and y in our similar triangles. So when we take the derivative with respect to time, the derivative of 17x is 17 dx dt, and that equals the derivative with respect to y, 11.5 dy dt. Substitute the value that you know. Dx dt is 7 feet per second. So we're going to get 17 times 7 feet per second is equal to, let's see, if I solve for dy dt, we're going to divide both sides by 11.5. Feet per second is our measurement. And then multiply in the calculator. We have 17 times 7. And then we're going to take that answer divided by 11.5. And we end up with approximately 10.35 feet per second is how fast dy dt, that's how fast the shadow is moving.